Hi everyone. Today's lecture we're going to discuss some of the more common measures of disease frequency that are used in epidemiology: rates, proportions, and ratios. We talked last time about the defining features of epidemiology. Quantification is one of these defining features. By carefully quantifying the burden of morbidity and mortality in a population, we can monitor trends in disease, evaluate health interventions, and begin to explore disease etiology. So if you picked up a clinical journal or went to the CDC website and searched for information about a specific disease, you might see a description that looks something like what I've posted here. And at first glance, it may seem a bit confusing because there are a number of different rates, proportion, and ratios. You also see some probably unfamiliar words such as case fatality rate, prevalence, and incidence. And so we're going to go through all of these different measures today. And by the end of the course, you should hopefully be able to pick up a journal article such as this and easily understand the epidemiologic language. Rates, proportion, and rates are commonly used in epidemiology. It's also important to note that many times they're used in clinical journals incorrectly. And so it's important to sort of quickly review the definition of each of the three and make sure that we're all on the same page as we move forward. A ratio simply is one quantity divided by another. There's no relationship between the numerator and denominator. And a proportion, it's a ratio, but those in the numerator are also in the denominator. A rate is a type of ratio, but there's a distinct relationship between the numerator and denominator, and there's a measure of time, and that time is very important, which we'll get to later. So let's start with ratios. Ratios are a fraction. There's a numerator and a denominator, but there's no relationship between the numerator and the denominator. So, for instance, we might be interested in the ratio between the number of male cases and female cases. And if we divide these two numbers, then we come up with a ratio of 19:1. So proportion, the numerator is a subset or part of the denominator, and it's typically written A over A plus B. There are no units to a proportion. It's always going to be between 0 and 1 and expressed as a percentage. So proportions are helpful if we want to demonstrate the magnitude of a problem. So for example, if we have 10 students in a dorm at ASU who develop hepatitis, how important is this problem? Well, if there are 20 students living in the dorm, then 50% of them are ill. But if 500 are living in the dorm, then 2% are ill. So that magnitude becomes very important. So this is a figure showing both the number of AIDS cases among female adults and adolescents and the proportion of all AIDS cases that are female. So these two measures tell us different but equally important pieces of information. So you see the absolute number or count of females with AIDS is increasing. This is shown by the yellow line. But the proportion of total AIDS cases that are female, shown by the blue bars, is holding steady. So we might expect the absolute number of AIDS cases to increase because the population of women is increasing. However, the fact that the proportion of AIDS cases that are women hasn't changed tells us that the mode of disease transmission probably has not changed too much recently. This might also tell us something about the effectiveness of our HIV prevention programs in trying to prevent AIDS in heterosexual couples. Okay, so let's talk about rates for a minute. Rates are a type of ratio, but they're different from proportion because there's a measure of time. So the calendar time period is the same for both the numerator and the denominator of a rate. The numerator is always the frequency of an event over a specific period of time, and then the denominator is the size of the population over that same period of time. And so in epidemiology, incidence and prevalence are two rates that are commonly used. So prevalence measures the extent or amount of disease in the population at any given time. We use prevalence in cross-sectional studies or in ongoing disease surveillance. And although we call it a prevalence rate, if you were paying close attention earlier, you'll see that it's actually a proportion. So the prevalence, for example, of Mycobacterium TB infection in the world was 32%, or the total number of cases divided by the total people in the population, 1.86 billion people with TB infection. Okay, so when do we use prevalence? Primarily if we're talking about the burden of a health population in a health problem in a population, so how many people have this illness or disease. If we want to talk about the frequency of an exposure, so we can talk about the prevalence of cigarette smoking or the prevalence of obesity or the prevalence of drug use. Prevalence is also helpful if we're trying to allocate health resources, such as facilities and personnel. So in areas where there's a higher prevalence of, say, diabetes, then we may want to allocate more resources to prevent and treat diabetes in those areas. Okay, so there are two types of prevalence. The first is point prevalence, and the second is period prevalence. So point prevalence refers to all cases of a disease, a health condition, or death that exist in a particular point in time relative to a specific population from which the cases are derived. So what does this mean exactly? It means that we calculate point prevalence as the number of cases of a disease present in the population at a specific time divided by the number of people in the population at that specific time. So if we were asking a survey question related to point prevalence, the question might read something like, do you currently have asthma? Yes or no? So period prevalence is just a little bit different. Period prevalence is sort of asking the question about how many cases of disease within a certain period of time. So period prevalence is defined as the number of cases of a disease, old or new, of a specific disease at a certain time, and the number of people in the population at that time. And so in a survey question for period prevalence, we might ask the question a little bit differently. We might say, have you had asthma in the past 12 months during the last year? And so that's asking about sort of the prevalence of asthma over a longer period of time, as opposed to point prevalence, which was asking about at this current point in time. So here's a graph of asthma prevalence among children 0 to 17 years of age by state. And this would be a typical example of how we might use prevalence data to illustrate health information. So when I look at a graph like this comparing prevalence rates across states, I'm always asking myself, why might we see the differences that we see? So why is the prevalence of asthma in Oklahoma twice as high as the prevalence of asthma in Arizona? Are there different environmental risk factors? Are there different household risk factors? Are there different diagnoses of asthma in certain states? So remember, these differences cannot be due to differences in population size because we're looking at proportion. So it must be something else. So the factors that can influence prevalence rates are several. And in particular, prevalence rates can be increased for a number of reasons. So if you live longer with the disease, you have a longer duration of the disease, the prevalence rate will be higher. This duration could be increased because treatments are better in certain areas. Maybe asthmatics have access to resources and medications in places, and they don't have the same access in other places. So the longer the duration of the disease, the higher the prevalence. You could have an increase in new cases. So the more cases that get diagnosed, the higher the prevalence will be. You could have an in-migration of cases. So people, let's say people with asthma could move from one state to another. For example, Arizona, for quite a long time, was home to some of the highest tuberculosis rates in the country. And that was because people with respiratory issues would move to Arizona because of the warm, dry air. You could have an out-migration of healthy people. So if your denominator of your prevalence rate is getting smaller, then the prevalence rate is going to get higher. And lastly, you could have improved diagnostic facilities. So if you have better reporting, more diagnoses, you're going to have a higher prevalence rate. Okay, so now let's shift from prevalence to incidence for a minute. Incidence rate describes the rate of disease in a group of individuals over a certain period of time. This period of time is included in the denominator. The numerator in an incidence rate is always the number of new cases of disease, and the denominator is the population at risk. So we define at risk as someone who's capable of developing the disease. So for example, if we were discussing the incidence rate of maternal mortality during childbirth, our denominator should only be women who are pregnant because they are the population at risk. So this formula works great if we're studying a fixed population where no one is allowed to come or go. But what happens if the people in the population that we're studying are under observation for different periods of time? So for example, some of the people in our research study might move out of the state. Particular example, we would need to do something different with the denominator of the incidence rate. So in the original incidence rate, we assume that everybody in that denominator was at risk for the population for the entire period of time under study. But now if we know that people are coming and going, we have to change the denominator. And so this denominator in what we call an incidence density rate becomes the time at risk instead of just the number of people at risk. So our denominator becomes person time of observation. So essentially what we're doing is we just add up the total amount of time that each person is under observation, and then that becomes our new denominator. So everybody contributes only the amount of time at risk that they were included in the observation time. So let me give you an example. If we were studying tuberculosis, we had one individual who's followed up for all 5 years in our study. They contribute 5 person years of follow-up time to the denominator. And we had another person in our study who moved away after 2 years. So they contributed 3 years of follow-up time to our denominator. So let's go through another example. Let's say we were interested in calculating the rate of injuries at a work site in a given month. So you can imagine that some workers might be employed full-time and others only part-time. So rather than count each individual equally, what we do is we count the total number of time that each person worked, and then we total this for all employees. So let's say over a 1 month period of time, we had 2 episodes of workplace injuries that were reported. Over that month, we had 100 different workers at the job site, but they all worked varying fractions of the month. And so let's say if we totaled up all of the hours that each of those 100 workers worked, they worked a total of 1,000 person hours. So we would calculate a person time rate, which is defined as the number of cases. So the numerator is the same as the original incident rate, the number of events, and then the denominator then is this total person time of observation. So we had 2 injury episodes, and we had 1,000 person hours of observation. So our incidence rate then becomes 0.002 injury episodes per worker hour, or alternatively, we could report this as 2 injuries per 1,000 worker hours. This is a graph from the World Health Organization showing changes in incidence rates of HIV infection around the world. Areas highlighted in red show an increase in the incidence rate over the last 10 years, and countries in green show a decrease in incidence rates over the last 10 years. And so by looking at changes in incidence rate, we can identify areas where HIV is spiraling out of control. We're looking at those red areas. And these might be areas where we would want to focus significant efforts on primary prevention efforts, such as maternal-to-child transmission intervention programs. The countries in green are seeing declines in new cases, so our prevention efforts have been successful, and these are places where the outbreak seems to be slowing down. So looking at incidence rates tells us something different than looking at prevalence rates. Incidence rates is telling us how things are changing, where the new cases are happening, so we can stay on top of the outbreak. So for those of you who are visual learners like I am, here's a simple little illustration that I like to use to help me think about the difference between prevalence and incidence. So if we think about a sink with a faucet of water, when we turn on the water in the sink, the water coming in, that's the incidence, sort of the inflow of water. And the prevalence then is the water level in the sink. So that water keeps going up and up and up. And the only way that you can leave that sink through the drain is by recovery or by death. So you can imagine that incidence is telling us all of sort of the new cases coming into a population, and prevalence is telling us, what that water level is, how many, which includes both the new and the existing cases. So for diseases that have a short duration, we're typically going to see a low prevalence rate compared to incidence rate. So this means that they're quickly leaving that prevalence pool, they're leaving the drain. And so these are diseases like an upper respiratory infection that you might come down with a respiratory infection quite often, but you get over it pretty fast. Foodborne illness, appendicitis, hemorrhage. So compare those to long duration diseases where the prevalence of those diseases is typically high as compared to the incidence rate. So something like diabetes or multiple sclerosis or Parkinson's, where they're not that common, but you live with that disease for a long time, the prevalence rate is going to be high. So there are always problems when we're reporting incidence and prevalence rates, things you should be thinking about in the back of your mind. They're not easy to calculate all the time. So we can have problems with both the numerators and the denominators in our rates. So on the numerator side, things that might explain differences across different areas. So why are those prevalence rates different in different states? It could be that there were different methods that were used to gather the data. So did people self-report that they had asthma? Were they given a breathalyzer test? Was there a hospital record? And so the method that you ascertain occurrence of disease may differ. Hospital records are also often incomplete, they're illegible, and they're not typically intended for research, so they're difficult to use. There could also be different definitions for disease. So maybe one group used a diabetes cutoff of 140 milligram per deciliter and another used 128. On the denominator side, sometimes selecting the appropriate denominator can be difficult. So, for example, what if we wanted to study accidents and cell phone use while operating a motor vehicle? What might be the appropriate denominator? Should it be the number of cars, or the number of drivers, or the number of trips, or the number of miles, or the number of minutes of duration of the drive? So you can see that the methods for choosing the appropriate denominator might also differ. So when you're comparing prevalence or incidence rates across population, you should also be thinking about the differences in methodology that could lead to those differences. So they might not always reflect true differences in disease status, but rather differences in the sort of the method of ascertainment. This is an example of a problem with the numerator. So this graph illustrates the prevalence of metabolic syndrome using two different definitions, the definition used in the US and the definition used in Europe. Metabolic syndrome is a clustering of risk factors for cardiovascular disease, so things like high blood sugar and high cholesterol and high blood pressure are included in this metabolic syndrome. And so NCEP is the US definition and IDF is the European definition. And you can see that the European prevalence of metabolic syndrome is much, much higher than the US. And it may not be that the actual prevalence of metabolic syndrome is different between the two countries, but rather that the way that we ascertain those cases is different. And this has important implications for policy, right? So are there really more higher cardiovascular risk, or are we just measuring it differently? So on the denominator side, in theory, the denominator of an incidence measure should only include the population at risk of developing a disease. So if we want to calculate the incidence of endometrial cancer in Arizona in 2012, what is our denominator? What should be the population at risk? I'll let you think about that for 1 minute. So the correct answer is that the denominator should only be women who have not had a hysterectomy. So if you don't have a uterus, you cannot develop endometrial cancer. So let's say the entire population of Arizona is included in our denominator instead. Would our measure of incidence that we calculate be too high or too low? So the answer is that it would be too low, because if we use the entire population in Arizona, the denominator is too big. And so if our denominator is too big, then our overall rate gets smaller. So you can see that you have to be very careful when you're calculating incidence and prevalence rates. So just to wrap up, although rates, ratios, and proportions may seem deceptively simple, carefully measuring morbidity and mortality in populations is an art as well as a science. So decision-making in public health requires good data. And just some takeaway points: a proportion is always a ratio, a rate is always a ratio, but a rate may or may not be a proportion. And rates allow us to make comparisons across populations, and we'll talk later about the difference between adjusted rates and unadjusted rates that you read about in your textbook. But this is another important thing that we do in epidemiology to sort of standardize comparisons across populations. So now that we know the basic language of epidemiology, we can start applying this language to look at some real-world health problems over the next couple of weeks.